Swayam Prabha. Digital India. Educated India.
Welcome to this course on Introduction to Robotics. My name is Professor Ashish Datta, and I'm a professor in the Department of Mechanical Engineering at IIT Kanpur, and I'm also the coordinator of the Center for Mechatronics here. So this course is basically an introductory course to robotics, and after taking this course you can take more advanced courses like robot dynamics and control, then robot motion planning, then robotics and machine learning, and courses like that. So we'll be talking about the very basics of robotics here, starting off with the fundamental transformations, then talking about sensors, actuators, basic control systems, a little bit of robot programming, kinematics, etc. So this course is Introduction to Robotics, and in this introductory course, in this introductory lecture, I'll basically talk about the history of robotics. Where did robots come from? The past, the present, and the future. Now, the lectures are divided into 12 weeks, and each of the topics for each of the weeks is given here. So in the first week, we have introduction, origin of automation, robot joints, classification of robots, and the work volume. Week 2, we have vectors, spatial transformations, rotation matrices, homogeneous transformation matrices. Week 3, we have DH parameters, how to assign axis to each of the joints, to be followed by forward kinematics and inverse kinematics in week 4 and 5. Then we have Jacobian singularity and manipulation ability in week 6, trajectory planning in week 7, and that will be followed by statics and dynamics of robot manipulators in week 8, and then linear control of robot manipulators in week 9. Force control is week 10, and then week 11 is manipulator mechanisms design, and week 12 is robot programming in VAL2. So VAL2 is the language which is used for programming most of the industrial robots today. So this is the basic outline. So every week we'll have 2 lectures and we'll have 1 assignment. The assignment will be related to the lectures. Normally the assignment will be solving problems or very short question answers, yes, no type of question answers. Now the reference books for this course is Introduction to Robotics. So this is the main textbook which I'll be following. So this has all the basic mathematics involved in terms of the transformation matrices, then forward kinematics, inverse kinematics, control will be from this book. We'll talk about sensors and actuators. So sensors and actuators is from the second book, Sensors plus Actuators. Is from the second book, that is Robotics Engineering. Then the control part I will be talking from the third book, which is Robotics by Professor Ashitava Ghoshal, and the fourth book is Industrial Robotics, Technology Programming and Applications. This is for the VAL programming part. So VAL2 programming of robots will be covered from the fourth book. So if you're planning to buy a textbook, that is if you want to study the subject of robotics in more detail, or you want to take this up for your master's or PhD work for doing research, then I would suggest that you buy this textbook. Okay, this textbook is one of the best textbooks. It is followed by in most of the courses around the world, and it is a collection of Stanford University lecture notes. So it is a standard book, and I would suggest that you buy it if you're going to study robotics further. Now, as we start off the course, the first lecture or introduction. Now, when you first hear the word robot, what is it that comes to your mind? So we hear of robots in various situations. For example, somebody can tell you that I work in robotics, or you see a robot in a TV or in a movie, okay, or you go to the shopping mall, and you see a toy and it says a robotic car or a robotic arm, okay, just toys. What is it that comes to your mind when you first hear the word robot? Now, for different people, different thing comes to your mind. For example, some people think that these are mechanical machines. Okay. Then for some people, it is like companions and friends. And for some, it could be pets and toys. For example, for younger generation, it can be pets and toys. If you ask a kid, what is a robot, he'll probably say a car which is avoiding obstacle and you can control with remote. That's a robot. Then it's very interesting that it depends on the age group of the person you're asking. It also depends on the background of the person you're asking. It also depends on which country you're asking. For example, in advanced countries, there are robots which are actually living in society. So if you ask somebody in Japan, they might even say a helper. Okay, a robot is a helper which is staying with an elderly person for providing companionship and doing simple tasks. And today, with robots coming into defense applications, a lot of people will also say that they are dangerous machines. Okay, so depending on your background, your age, your country, your answers could be different. But you will most certainly have an answer that if somebody says, what's a robot, you are likely to say something. Okay, so this is an interesting part, that robots have pervaded into society in different ways. Now, we talked about the past, the present, and the future. So when robots were first invented around 1950s, and from that time, robots were basically installed in industrial applications, mainly in the automobile industry, to do repetitive tasks like spot welding, spray painting, pick and place. Okay, and even today they do that. So this is the past of robotics. They were basically industrial manipulators to do industrial jobs in industries. Now, this is an example of an industrial robot which is doing spot welding in a car body. And these are industrial arms. They have multiple degrees of freedom. They can go to different locations and they can do tasks like spot welding. So this is something that is most common that comes to your mind if somebody says that this is a robot. Now, so this is the past. It is also at present what about 80% of robots do. They work in the industries for doing automobile assembly or in the electronics assembly in electronics industries. Now, the interesting question, what is the state of affairs as far as the present is considered? In the present, basically robots are used in warehousing, in online shopping, for example, Amazon. So when you place an order in Amazon, what happens is you place the order using a software in your laptop or your phone. Okay, and then that order goes to Amazon. Now in the Amazon workhouse or in the warehouse, what happens is your part or your product would be stored in some rack. Okay, and so this is showing an Amazon, this is showing the inside of a warehouse. So there are thousands and thousands of parts which are placed in different locations or different pods. And when you purchase an item, what happens is this is sent onto your warehouse. And in the warehouse, the software sends a robot to go and get where your part or your product is located. So the robot has to go to that particular specification or location and get the product and bring it to the delivery station where it is packed and then sent to you for delivery. So what do these robots have to do? These are mobile robots. They have to retrieve the pod, and they lift the whole rack and they bring it. And how many robots are there? There are a very large number of robots, say 2,000 to 3,000 robots at the same time. So you can imagine what this involves. It involves motion planning. The robots have to drive and not hit one another. And it should be optimal. What is optimal? If there are 3,000 robots working, then it should take the shortest time to get a part and then deliver it to you. Okay, so this is an example of a mobile robot. The previous example I gave was that of an arm robot, a serial arm. Okay, so this is where we are at present in terms of robotics, where our interest is where we are connected robots in some way. And this is how the Amazon workhouses and a lot of the retailers work these days. So this is the present of robotics. Okay, so the past, the present. Now this also brings us something very important and very interesting, is that we may think that robots are not connected to our lives in any way. So if somebody says, are you interested in robots? You may say that I have nothing to do with robots. But the reality is that you are connected to a robot. Whenever you're buying something, a robot is doing something somewhere. It need not be a hardware robot. It could be a software robot, which are called bots. Okay. For example, a chat bot, when you're chatting with somebody, how do you know it's a human on the other side? It could be a machine. Okay. It could be a computer program or a robot, which is actually chatting with you. So the past is industrial arms like this, okay, doing jobs in industries. Even today, these are there. This is where it started off. Then at present, we are in this automatic warehousing, which is the present. And companies like Flipkart, Amazon, they use this extensively. robots are of different types. You have seen an arm robot, which is here. Okay, this is having multiple degrees of freedom doing tasks. This was in this particular case, it was a mobile robot. So past, present, future. What about the future? There are a lot of robots which are living in society today, okay, in many countries in different ways. Chatbot is one example, but that's a software-based robot. In terms of hardware-based robots, there are a lot of robots which are coming in the form of guides, in the form of teachers or as companions, pets. For example, this one on the right side is a robotic teacher for interacting with kids. Okay, and this is another robot which is essentially made for giving directions in an airport or in a museum. Okay, now some people have also ended up making clones of themselves, so robots which look like them. Now it's very interesting that in this central figure, it's very difficult to say which is the robot and which is the human. So is this the robot or is this the human? Okay, how do you know? So it's very interesting. This is the direction in which robotics is going. So what I'm trying to emphasize is that we are connected to robots in different ways. And you may think you're not connected, but actually you are connected. So it's a good idea to study robotics and having some idea of robots. Okay, because this is the direction in which the future is going. Now, in terms of industrial robots, our industrial manipulators were arms of this nature, okay, for doing tasks. Now, these arms are kept inside cages or boundaries. So, for example, if you see here, there is a boundary here, and the robot is inside the boundary, and there are no human beings here. The human being has to be outside the boundary. Now, that is basically for safety, because these robots are industrial robots. They're very, very strong. If they were to hit a human, okay, then the human can be very, very seriously injured. So as per industrial laws today, the robot and the human do not come in the same workspace. Now that is another thing which is changing, is that future robot design would be such that the robots should be safe so that they can work with humans together in industries. How this helps is essentially it saves time, so the robot and the human can do the task together. Also, if a robot is, let's have a look at this kind of robot. Okay. So if it's this kind of a robot which has two arms, the internal structure is not like that of industrial robot. It is safe. The programming can be done very easily. The human can take and push the robot, as you can see, and the robot can learn from there. If it hits somebody, it's safe. So if it hits, it'll immediately stop, it'll change its direction. Okay. So this is a very simple way of programming where the person holds the robot, moves it around, and it can learn what task is required for the robot to do. So this is the direction in which robotics is going. Design safe robots, do safe programming, and enable robot-human interaction. So in terms of industrial robotics, the future is in making robots safe so they work with humans in industries. In terms of social robotics, this is social robotics, where to make robots which are similar to humans and can do particular human tasks like human beings and almost behave like human beings. So these are two directions in which it is going. One is social robotics, one is industrial robotics, where the human factor is coming in between. Okay. Now, as we are at this topic, these are interesting questions that come up, which didn't exist probably 20 years ago. But today they are there. For example, if you're talking about a robot in human living in society, okay, should it be a male? Should it be a female? Should it be neutral? Suppose you're buying a robot to a robot toy, okay, you might have to answer some of these questions. Now, these questions are funny, but they are relevant today. Then the other relevant point is the last line here. What laws should be applicable to robots interacting with humans? Okay, so suppose there is a robot and human working together and there is an accident and the human is hurt, then who's responsible? Is the robot responsible or is the human responsible? What kind of laws govern this? Okay, so these are some funny questions that have come up because robots have come so much into society today. Now, historically, robotics is a part of the larger subject which is called automation. Okay, and this business of automation has been going over for thousands of years. It is not that suddenly one day somebody woke up and invented automation and there is a eureka moment and the person says, okay, this is automation. So it's nothing like that. This process has been going on for thousands and thousands of years. And the definition of automation is essentially replacing human muscular power. So any task, machine, or activity which replaces human muscular power can be called automation. And this process of automation has been going on right from early days like 10,000 BC. Okay, this is very, very long time ago, where human beings made tools to make their life simpler. Okay, and initially they made stone tools, then became iron tools, then became copper tools. So tools were used to make better tools, and human beings are tool makers, and tools make better tools. Okay, so in terms of the Stone Age, we can say stone tools, iron tool, copper tool, like that. In terms of today, we can say NC machine, we can say CNC machine, then we can say SIM. So these are also machines, these are also tools, and tools are making better tools. Okay, and this process has been going on, and this is a process of automation. Robotics is a part of the bigger process of automation. Now, so 10,000 BC, human beings were making different kind of tools to make their life easier. Now we come a little bit more ahead, 150 BC. Okay, so where very simple kind of automatic devices were made, like the steam engine, Heron's door. Now this is the earliest example of the steam engine. So there would be a container containing water, and they would burn fire. And what would happen is the water would be converted to steam. And these are two pipes. The steam would come through these two pipes, and there are two exhausts in two directions. You can see this is one direction, and that is another direction. The exhaust from this hemisphere, and this hemisphere is mounted about an axis. So when steam would come out in these two directions, what would happen? It will generate a moment there, and this hemisphere will start rotating. Now this is the earliest example of a steam engine. Okay, and if you see the date is 150 BC. This is very, very long time ago. Now the other example is the Heron's door, automatic opening and closing of doors. So how this works is they would burn fire here, and this fire will heat the air inside this container and increase the pressure there. Now when the pressure here increases, what will happen is the water from here will be forced into the bucket which is here. Okay, so when the water flows like this, the weight of the bucket will increase, and it will tend to pull the bucket down. Now the bucket is connected through wire rope and pulleys. Okay, and when the weight of the water here increases, the force, downward force, will increase, and because of which this will start rotating. So this will rotate, and if this rotates, what will happen? The door will open. Now when you put off the fire, what would happen? The pressure will go down, because of which water from here will go back there now. And when the water goes back, the bucket will go up, because there is a corresponding weight on this side. Okay, this weight will pull it down, the bucket will go up, and the door will close. So this is the earliest example of an automatic door opening and closing. So what we are seeing is that automation existed from very, very long time in different ways. This is one of the earliest examples, 150 BC in Greece. Now, as we go further, about 1780 saw the creation of automatic dolls, which could write, draw pictures. These were mechanisms basically, and they had some kind of a key. So if you wound up the key, there would be a spring inside. That's where the energy gets stored in the form of potential energy. And these dolls could move in different positions and do different things. Some of them could write, some could draw pictures. Okay, these dolls are there even today in some of the robotics museums around the world. Now, as we progress further, 1801 saw the creation of a program textile loom. Now, you would have seen this textile machine which is used even today, textile looms, and how the weaver sits there and operates the machine is, suppose this is my cloth and there are some designs in the cloth, for example. Now how this design is being made is the thread is being moved. Okay, so the thread is starting from here, then it moves like this, then it moves like this, and as the cloth is being weaved. And how that is done is there is a handle, and this thread comes through the handles, right? You would have seen this either in actual or in TV. And by pulling the handle down, the person changes the location of this thread and hence creates this design. Now what this gentleman James Chera did in 1801 is he embedded this design in the form of a punch card. Now what's a punch card? A punch card is something like the OMR sheet that you use these days. So there is a hole, there are circles or bubbles, and either you make them black with a pencil or you leave them. So for example, when you're answering a question 1, 2, 3, 4 like that. Okay, so you can leave it blank or you can encircle it using a pencil. Now this will probably mean 1, this will probably mean 0. So a machine can read a 0 or a no 0. So essentially darkened black or a white black, or darkened hole or a hole which is not darkened, and it can assign 0 and 1. So basically what this gentleman did is he made a punch card. So this is basically a punch card, and there is a hole or a no hole. So wherever it is supposed to be black, there is a hole which is punched. And in another case, if there is no hole, there is no hole which is punched. Essentially, it is again a 0 and a 1. So a punch card is the earliest way in which a program could be written. Okay, so a punch card. And this is a punch card which is shown here. So you can see that there are lines and there are holes or there are no holes. in this row of hole. So this is the earliest example of a program being written in a punch card, and the early computers, NC machines, all use punch cards. Today we don't use them anymore, but this is where it originated. So we see that the punch card was first used in the manufacture of textile by Joseph Jacquard in 1801 in France. And that is the creation or the development of a programming, a way of writing a program and storing a program. Now, as we move further, 1904 saw the creation of, or the invention of, a transfer line. What is a transfer line? A transfer line is used in assembling cars even today. So if you go to any car company, what you'll see is that there are conveyors, and the car body or the chassis sits in the conveyor, and the conveyor moves, and it comes and stops at different locations. And at every location, there's a human being who does something, or a robot which does something. Okay, so this is the idea of a transfer line, and it was invented in 1904 by Henry Ford in the Ford mass production of vehicles in the US. And even today, this is used. Now, we have come till 1904, but there is no robot till now. These are basically mechanisms or mechanical devices. Okay, so there is no controller, actuator, sensor involved anywhere. Of course, the computer is not there at all. Now, as we move further, or before moving further, let's look at where the word robot came from. Now, in 1921, a Czechoslovakian drama writer or playwright, Karl Kapek, he wrote a play in which he depicted human-like mechanical men to do dirty work in industries. So apparently this is a picture from his play, and there is this mechanical man, okay, which is going to do dirty work of human beings in industries. And he used the word robot there. So this is the invention of the word robot, okay, or the first use of the word robot. And it basically means mechanical men or a slave man for doing dirty jobs in industries. 1921. 1942, Isaac Asimov used the term robotics. So Isaac Asimov, you would be familiar with, some of you might have read his books or seen his movies, where he said that in future there will be a subject called robotics, and there will be all kinds of robots. And he wrote a lot of science fiction stories that what would the human civilization be 200 years or 300 years from now. There's a very interesting movie called I, Robot. You can see it, that is supposed to be a robot 200 years from now, what it will be like. He also formed the 3 laws of robotics. And it's very interesting that in 1942, there is no robot, and yet he could imagine that robots will be like this. And this is what the future of robotics will be like. That is fascinating. Now, 1942, of course, till 1942, no robot. Okay, we only have transfer lines, which are mechanical devices. So where did the robot come from? So in 1945, during the Second World War, they had to make the atom bomb. And for making the atom bomb, they had to handle radioactive material. For example, plutonium and uranium. And human beings could not go near it. So in order to handle this radioactive material, they made this mechanism or a master-slave manipulator. Okay, so how this works is there is a master on the left side. So there's a master and there's the slave. And the master and the slave are identical in terms of the number of joints they have and the number of motions they can do. And in between the master and the slave, there is a very thick wall, and with a very thin slit in there, or a window, which is filled with oil. So this is going to be concrete. Okay, and a concrete wall. So radiation from this side cannot go that side. And this is a very thin window, glass window, which both sides of it, so there is glass here, and inside it is filled with oil. So again, radiation cannot go from this side to this side. Okay, now how it operates is there would be a master who would be standing there. Okay, so let's say this is the master. Okay, so this is my master who is holding this and is standing there. Okay, and every joint is connected to the slave side. So when the master pulls it like this, what would happen is this connection is connected, this joint is connected by wire rope, it goes through like this, and the wire rope goes to exactly the same joint on the other side. So when he pulls it like this, what will happen, the tension in the wire will change, and because of the change in tension, this arm will also move like that. So there are 4 or 5 joints, and the master can be operated by the operator. So there is an operator there. And whatever the operator does, the slave also does the same thing. So you could do very simple tasks like pick and place an object, go and pour liquid into a glass, but not complicated motions by using this master-slave manipulator. Now, more importantly, this is strictly a mechanical device. There is no controller, there is no sensor, there is no program, there is no computer, of course. Okay, so this master slave manipulator is called the father of the robot, and it is used even today in atomic energy establishment, in nuclear power stations. This is still used today, where they have to handle radioactive material. Now, as we go further, 1945, we see master slave manipulator, but something happened, or something was invented somewhere around 1949, which created, or which combined mechanical engineering with electrical engineering, and things became electromechanical. Okay, so what was invented in 1948-49 that changed everything? Okay, now this is what I'm trying to show, is that there were three major changes that took place, and these three changes changed the subject of robotics, and changed technology. Not only robotics, it changed industrial applications all around the world. Okay, now if you look at what were the inventions, we also understand why it changed like that. And it's important for us to look at these changes, because we can predict the future and see what the future would be like if we understand what were these inventions and how they impacted society and technology. So the first was the creation of or invention of the transistor, 1948-49. And with the invention of the transistor came the concept of a computer, and with a computer came the concept of reprogram. Okay, so till now there was no computer, there was no program or reprogram. Okay, so mechanical device could not change what it was doing, because there was no reprogramming, there was no program at all. Okay, there were no sensors, actuators, controllers there now. So with the transistor came the concept of reprogram, and from here was born the first robot, which is called Shaky. It is shown here in the figure. So the first robot was invented in Stanford University. It's a mobile robot which can move around and do simple tasks like obstacle avoidance. And 1952, George Dowell invented teach and playback devices for NC machines. So NC machines and robots essentially are the same technology. Okay, in a robot, you move a robot by inserting numbers, which are the position coordinates of the arm or the end effector. And in the case of NC machine, also you're moving a machine tool, or you're moving the part, okay, by inserting numbers. So NC machine also means numerical control. And this is what we mean by a robot and an NC machine being the same technology, essentially. And they all came out because of the invention of the transistor. So from 1950 to 2000, it's not very long, it's 50 years, and today is 2020, so it's about just 70 years. So it has moved from a very simple mobile robot, having few degrees of freedom, doing simple tasks, to a very complicated device like this, which has very large degrees of freedom. It has speech recognition, it has some amount of AI, it has vision processing ability, it can walk, run, do all kinds of things. Okay, so how do we go from here to here in 70 years? That is what we'll look at. So the first was the invention of the microcontroller, or the transistor, which resulted in this creation of this mobile robot. And then two more major changes came, because of which it went from here to here. Let's look at what they are. So after the invention of the transistor, we had the computer, and the early computers were so big and they were not very powerful, they consumed a lot of energy, because of which we had one machine, one computer controlling one machine. Okay, so we have a program, we have a machine control unit, which is a computer here, okay, controlling one machine tool. It can be a machine tool or it can be a robot. Either way, it is the same. So we have one computer controlling one machine, because the computer was not powerful enough to control more than one machine. Now, as time went by, the computer became more and more powerful. And as it became more powerful, it could control many machines that you can see here. Okay, so it's one computer, one machine. Here there is one central computer, and it is controlling many machines together now. So essentially, the computer is becoming more and more powerful. From NC, we go to CNC, then we go to SIM, okay, in that order. Now, as the computer became more powerful, it could control not only more machines, but different kinds of machines. So here it is controlling a robot, a machine tool, a work table, parts carousel. There can also be an AGV, okay, automated guided vehicle, which is bringing parts and putting it on the carousel. So it can control all of these things together. Essentially, because it is becoming more and more powerful, it can have more sensory input-output in terms of sensors. And then from there, it moves on to computer integrated manufacturing. So we have NC, CNC, DNC, FMS, and then computer integrated manufacturing, where the robot not only integrates or controls where the computer not only controls uh, one robot or one machine tool, but it integrates this with other functions of manufacturing. For example, material resource planning, material arrival, departure times, okay, scheduling. So the computer has become powerful that it is integrating manufacturing with other aspects of manufacturing. Okay, and as we move around, we have 4 industrial standards today. Okay, so we have industry 1.0, 2.0, 3.0, 4.0. This is how industrial standards or industries are divided. Okay, and this division essentially comes from the driving power. So here it is stream power driven. All industries belonging to 1.0. So this is about 1700 or 1600 or before that. So before say 1800. Okay, all the industries were driven by steam power or water power. Okay, and these come under classification of industry 1.0. Now in 2.0 we basically have mass production assembly lines, and the essentially driving power is electricity. So this is the industrial revolution about after 1800. Now as we move on, the computer came about in 1950, and then we had computers and automation, computers controlling automation, and we also call this the IT age. This is about 1970s. Okay, where we have computers controlling robots, different kind of automatic machines to do particular tasks. And then we move further to about 2000, where we have industry 4.0. Now the difference between 3.0 and 4.0 is there is computers automation in 4.0 also, but there are also humans, and there is some amount of intelligence involved. So it is like IT plus humans plus intelligence is what we are getting in which is making it industry 4.0. As I said, that the direction in which robotics is going is that the robot and human should work together. So it basically means that a human is in the loop now, and there can be some kind of virtual world. It is also called cyber physical system in some way, sometimes, but it essentially means that there is a connection between machines, humans, and there is some AI, okay, involved. So this is the direction in which industries have gone. In terms of robots also it is the same. Now it's interesting to note what is the definition of a robot. Now nobody seems to agree. Why? Because different people would like to call their system or their invention or their whatever they are doing to be related to robotics. It is fancy, and it has more impact. For companies, it's a marketing impact. For students, it sounds good if they say we are doing research in robotics. Okay, so most companies will tend to call their product a robot. So it is so it's become important to know that what is a robot and what is not a robot. Now unfortunately there is nobody seems to agree on that, but in general, to be called a robot, a system should do some or all of the following. Let's look at these 3 things that a system should be able to do to be called a robot. Now the first is what is the meaning of moving around. We saw that the Amazon workhouse, the robot is moving around. Okay, a serial arm also moves around. Okay, so we understand what it means. The second is sense and manipulate the environment. Now a robot can sense a mobile robot can check if there's an obstacle in front and change its direction. So the second is sense and manipulate the environment, and third is display intelligent behavior. This is easy to understand. This is also easy to understand, but this one, the third one, is not very easy to understand, because what is the meaning of intelligent behavior? Okay, there is no standard definition of intelligence. Okay, and the vague definition of intelligence is it should be able to think like a human. Okay, so intelligence would mean it should be able to think like human, or behave like human. Now that is a very wide definition, so it's not very clear what it means. But if a machine has some amount of intelligence, so you can call it a robot. In that sense, we have software robots which are called bots, like chat bots. Okay, so when you're chatting online, okay, you're not very sure whether it's a machine who is answering or it's a human being. Okay, so that would mean that it should be able to display some kind of intelligent behavior. So to be called a robot, it should do some or all of the following: move around, sense, manipulate the environment, or display intelligent behavior. Now by these 3 requirements, is a CNC machine a robot? That's an interesting question. Now a CNC machine does not move around. Okay, then it does not sense and manipulate the environment. It does exactly what the program tells it to. and it does not display intelligent behavior. So because of this, a CNC machine is not a robot. Now, what about the Amazon robot? Is that the which we saw some time back? Is that a robot? No, yes. Why? Because it moves around. The mobile robot moves around. Does it sense and manipulate the environment? Yes, it will have sensors. So if there is an obstacle, it can immediately stop or change its path. Does it display intelligent behavior? Well, that depends what you mean by intelligence. Okay. So in a way, maybe a little bit, because if it can sense and manipulate the environment, it also needs to take decisions on its own. Okay, so in a sense, maybe it has very little intelligence or maybe no intelligence, but it satisfies the first two. It moves around and it senses and manipulates the environment. So we can call it a robot. So if you look at these three requirements, then if a machine satisfies any one or all of this, we can call it a robot. So there is automatic vacuum cleaner. Is that a robot? Yes, that's a robot. It moves around and it senses and manipulates the environment. Automatic wheelchair, is that a robot? Yes, that's a robot also. Okay, so this is basically to define what is a robot. Now, since the early 1950s, we have had 3 generations of robots, and this definition of generations of robots basically depends on the amount of interaction it has with the environment. So the first robots did not have any external sensors. They could not interact with the environment, and they were very simple pick and place kind of devices without any kind of external sensors. The second generation had external sensors like vision, tactile for interaction with the environment. And the third generation are what we call intelligent robots. They can have some kind of thinking capability maybe, or decision making capability. They can be made up of smart materials, then biocompatible materials, etc. And future robots is biorobots, micro, nano, cyborgs, androids. Some of them are science fiction, some of them are there already. So this is the direction in which robotics has gone. First generation, second generation, third generation, and then future robots. Now the first generation robots, 1950 to 1970, they are simple pick and place robots without interaction with the environment, and they can be divided into different types of robots depending on their structure. We'll come to this in more detail as we go along, but this is just to show they can be Cartesian robots, they can be cylindrical robot, they can be spherical, they can be SCARA type, they can be articulated. Okay, and these are robotic arms for doing particular applications in industries. Okay, so this is an example of how robots are divided. The first generation robots are divided based on their structure. So this is 1950 to 1970. Now what happens after that, about 1970s, is that electronics became smaller, faster and cheaper. Now this means that things like cameras, computers, processors became faster, they became smaller and they became cheaper, because of which people started using a lot of these external sensors for interaction with the environment, like vision, advanced sensors, advanced controllers, microcontrollers, DSP, speech recognition, AI. Okay, so essentially the second great revolution that took place was the electronics becoming smaller, faster, cheaper because of VLSI. Okay, very large scale integrated circuits. So all the earlier vacuum tube, diode, triode, which was made and assembled in different places, they took up a lot of space, they took up a lot of energy. But with VLSI, you could make everything on a motherboard. Small chips could be assembled and you have one motherboard which can do everything. As a result of which, computers became smaller, faster and cheaper. Today, we can buy cameras which are very cheap, 500 rupees, you can buy a very good camera. And it is so good that we can do very good image processing with that. And this you know that electronics has become very small, it has become very fast, and it has become exceptionally cheap, because of which their applications in robotics have also progressed very quickly. So the second revolution was electronics becoming smaller, faster and cheaper. Now actuation in robotics and numerical control basically has this kind of structure. So we have a controller, then we have an actuator, which is a motor. So there's an actuator. Then we have the work table or link, which is the one we want to move, and there is an encoder or a position sensor. Okay, so this is the closed loop control structure of an NC machine or a robot. So there is a controller. The controller actuates the actuator, which is a motor in this case, and the motor rotates, moving the work table or the link. And as it is moving, the feedback comes from the position sensor and it goes back to the controller. Okay. Now, if you think a little bit, if you want to make a very small robot or a very small machine, would this structure still work? What I'm saying is, if I want to make a very small robot, how small is small? Nano? less than a millimeter, micro less than a millimeter. Suppose I want to make a very small lathe. Small is how small? Maybe 20 square millimeters for that size. So that size is 20 square millimeter, 20 millimeter cube, let's say. Yeah, it's a cube machine. So in that case, can I take this structure, shrink it, and make a lathe which is 20 millimeter cube, and will it still work? The answer is no. If you think a little bit, the answer is no. Why? Because if you start shrinking the actuator, let's say it's a DC motor, if I make it very small, after some time it will not work anymore. Okay, because after some time it will not be able to produce force to move or to cut material. So if you want to make a lathe very small, or you want to make a robot which is very small, then you cannot take the conventional actuators, shrink them and make small actuators. They don't work like that. Okay, so what we can do is we need to use actuators which are not AC DC motors, but we need to actuate it in some other way. Okay, and that is the third revolution. Okay, first revolution is transistor, second revolution is VLSI, third revolution is new materials. So new materials, smart materials, were used to make smart actuators, smart sensors, and this is what gave rise to making very small machines which can work in the micro domain, nano domain, vision, biorobotics, etc., etc. Okay, so these are actuators which are smart, made of smart materials. For example, piezo is one. As we go along, we'll see what these are. Piezo is one, then ionic polymers, electroactive polymers, shape memory alloys. Okay, these are actuators which are made of smart materials, and they are independent of the size of it. That means if I make them very small, they will still work. Okay, and because of this, we could make robots which are very, very small for doing different applications. So these are the three generations of robotics that we have seen. The first is transistor, then we have electronics becoming smaller, and then smart materials, which has taken us right from industrial robots to the nano micro domain. There are other ways of classifying robots. So one way of classifying robot is by the external interaction. So we have generation 1, 2, and 3. Other ways of classifying robots are parallel robots and serial robots. So the name indicates parallel robot. So this is a parallel structure. You can see that it can move. It can move with this piston cylinder kind of mechanism, and the base is fixed, and the other end, the top part, is also fixed. So this is a parallel device or a parallel robot. This is a serial robot where the end effector is not fixed. It is free to move in space. Okay, so this is a serial arm robot. Then we can have mobile robot, or we can have stationary robot. So this robot is a fixed robot which is not moving. This is also a fixed robot which is not moving. But we can also have robots which move around. For example, not moving, I mean the base is not moving. The arm is moving, yes, otherwise it won't be called a robot. But then the base is not moving. Whereas this is a mobile robot, this is an aerial vehicle, this is a drone. So these are robots which can move around, fly around and move around. So we can have stationary robot arms, or we can have mobile robots. This is another way of classifying. Another way of classifying is industrial robot and social robot. So this is an industrial robot, where these are social robots. Okay, so robots can be classified in different ways these days. Now, what are the future? Now, in the future, there are different robotic applications, and a lot of these applications have to do with social requirements and social needs. For example, biorobotics, emulating biology in the nano and the micro domain, exoskeletons, wearable devices which can be worn to augment strength and endurance, neurorobotics, androids, cyborgs, robotic drugs, nanorobots for curing disease, surgery, assistive rehabilitation robotics, outer space, nuclear. So outer space and nuclear has always been there because human beings cannot go there. Okay, so they always require robots. Defense, again, there is a growing demand for robotics in defense because everybody would like to save the life of a soldier. Why put a soldier or put a human being's life at risk? Replacement of body functions, then Internet of Things, cyber physical systems. These are new, and in future, whatnot more is going to come up. Okay. So this is the future of robotics in which it is going. Some examples. So this is a robot which is very, very small. How small? The robot is so small that it can go inside the blood cell. So these are the red blood cells. You can look at this. Red ones are the red blood cells. So the robot is so small that it can go inside in the blood vessel and then it can perform a particular function. For example, if you want to kill a particular virus or you want to kill a particular cell, so this robot can be injected inside the blood vessel. It will go to that location, kill the tissue, and then come out. So we are already at that scale. Robotic surgery. So you know that bypass surgery is a very painful procedure where they have to cut open the chest and then locate the artery which is blocked and then make a bypass. Whereas in this case, what is done is if there is a blockage in the artery, the robot can go in and it can drill holes and remove the blockage. Okay. Now we are already at that scale. We already have robots which are that small. They can be inserted through your through the veins in the hip or the thigh or the arms. And in the case of putting stents in the heart, these are already there. They can insert it from some part of your body, guide it there, and then it can go to the particular location, do the task, and bring it out. What is the problem with this kind of robot? We are already in that scale. We can do drilling. But the problem here is if you start doing drilling like this, the material which is drilled off, that will start going to all other portions of your body, right? So the robot is drilling, that's fine, but the drilled part is going to start floating around now in your bloodstream, and it can go to your brain and clog up some artery there. Okay, so although we can do this, it is still not very clear how to remove the debris from there. Okay, that is an interesting point of research which is still going on. So robotic surgeon, robotic dentist, some of these ideas are very funny. Okay, that why would somebody make a robot to clean your teeth? Again, the question is the cost. If you can have a robot which can do grinding on your teeth and it costs less, then people are going to use it, right? So this is the reason why a lot of companies have started doing all kinds of funny things which are not really industrial, but you can make a lot of money by doing this. Okay, so robotic dentist is one example. This is another example. Robotic haircut. This is there in many countries already. Okay, so it is something like a cap. So they will take the cap and put it on your head, and there are small cutters inside which will cut your hair in a particular shape. Okay, and again, why would somebody make this? Why would some company make this? It costs much less to do this than to do this with a human, especially in developed countries. So in the US, probably a haircut is $50. In India, it can be 50 rupees. So if a company can make a robot which can cut in $10, then it is going to be cheaper, and because of which it is already there in several countries overseas. This is an example of a smart actuator I talked about. So a smart actuator like an electroactive polymer. So this is a hand which is made with a smart material called electroactive polymer. And by giving voltage in two sides, you can make it bend in a particular way. Now you can see there are no joints anywhere. Okay, there's no sensor actuator. The linkage itself is an actuator, and it's also a sensor. Okay, so this material is electroactive polymer. It's Nafion here. By applying a voltage in a particular direction, we can make it bend in a particular way. Okay, if you reverse the voltage, it will bend backwards now. Okay, now this is independent of the size effect, which means that if you cut this, you can make a very small robot which will behave like this, and it has nothing to do with the size because there is no DC motor there. So all the micro and the nano applications normally use smart actuators for actuation. We'll come to part of this when we talk about sensors. These are other examples of smart material based actuators and sensors. So this is again a bird, and this is a snake which is made of a smart material which can change its shape depending on how you give voltage to it. Okay, again, no sensor, no actuator, no linkage. This is an example of exoskeleton or enhancing human muscular power, where the person can wear a robot and it increases his or her strength to carry object or to go up or down the stairs, which is called an exoskeleton. This is a robot again which is used for rehabilitation, for training, gait training. That is, persons who are paralytic, who have suffered stroke, they need to be taught how to walk. Now this is a robot which can teach you how to walk. Automatic transport. These are buses which don't have drivers. They move automatically and come and stop in particular locations. People get up, get down, and they go to the next location. So this is automatic, or it is a robot. Why? Because there is no human intervention. There is no human in there. Okay, no human in there means there's no human driver in there. Okay, so autonomous transport is already there in many countries in the world. More funny questions. Happy robot, sad robot. People in computer science are studying things like behavior. Okay, how should a robot behave? Should it be happy? Should it be sad? So if you're going to buy a robot, would you like a happy robot or would you like a sad robot? This is a funny question, but it's relevant today, because if you say happy, then when you are sad and the robot is happy, it doesn't make sense. Or if the robot is sad and you are happy, again it doesn't make sense. So it means that basically the robot should be able to adapt its behavior to your behavior now. Okay, those are directions in which people are looking in terms of behavioral robotics, neuro robotics, and things like that. Brain-computer interfaces. So if you can take the signal from the brain, so whatever task we perform, we first think in the brain, and then it goes down to the hand or the leg, right? So if I can record this thinking right from the brain and use this to drive the robot, for example, if this is a monkey or a human being, at the present moment, how do we play a game? We basically use a joystick, and by moving the joystick, you move the robot or you control the game. Now, suppose we have a brain-computer interface which can take the signal straight from your brain. And if you want to, say, for example, in this case, you want to move the robot right, and you're thinking, move the robot right. If the controller understands that, then it can take that signal from the brain and it can move the robot on the right side, right? So there is no joystick or any other interface involved. Automatic road tracking. These are automatic cars. Today, there are a lot of Google cars and Apple cars which are there. A lot of companies are actually trying to make autonomous cars. Ford is trying to make, even in India, there are companies trying to make autonomous cars. And these cars have to track road conditions. Okay, so these are autonomous driving, and it's a robot in a way. Although they say it's an autonomous car, it is actually a robot. Driver tracking. So is the driver feeling sleepy? Is the driver talking on the phone? Is the driver distracted? So these may not be directly a robot, but it could be software which is automatically tracking the driver. This is also a bot of some kind. Ethics and laws. Okay, so we talked about robotics in different ways. Now, what we need to understand is that, is this machine a robot? How do you classify? You have to look at those three rules. Does it move around? Okay. Then does it have some kind of intelligence? And does it have sensory input output with the environment? In most of these applications, you'll find that there is sensory input output with the environment. The system moves around and the system displays some kind of behavior or intelligence like a human. Okay, very small amount, but it is there in some form. And hence these devices can be called robots. Now, with all this has come the requirement that ethics and laws. So when there are robots which are living in society, okay, what are the laws that should govern them? Okay, so this is another area where people are now looking at it, and because of which robotics is not only limited to people in engineering, okay, or computer science, but all the other disciplines are getting involved: sociology, psychology, okay, legal aspects. Because if a robot is going to live in society, there are all kinds of psychological issues. There can be social issues. There can be ethical issues. Okay, so all of this have got together, and today robotics pervades not only engineering disciplines but all other disciplines, including the sciences and the arts. So robotics is going everywhere now. So even people who think they are not involved with robots are actually involved with robots in some way. Now let's remember this. This is one of the famous quotations which I like a lot, that Isaac Asimov had actually said that in 200 years the robots will take over. Okay, so let us remember this, that one robot can do the task of 100 men, but 100 robots cannot do the task of one extraordinary man. Okay, and you have to be the extraordinary man so that robots do not take over. So this is very interesting, and we have to keep this in mind. Now, moving on further, next we'll be talking about robot joints and work volume. That what are the different kind of joints which are there, and by connecting different joints, how can we make a robot? Okay, so how does the robot essentially work? A robot has joints, so these are joints. So this we can call as joints, and these joints are connecting with links, and the base of the robot is not moving. That's the base and not moving. Okay, so in this course we'll be dealing only with serial arms, and in this serial arm the base is not moving, it is fixed. There are links. The links are connected by different kind of joints, and this is called an end effector. Okay, and there is a controller which can be a PC or a microcontroller. Okay, and this is my controller. So these are the elements that make up a robotic system, and we'll look at them one by one as we go along. We'll start off with joints, then we'll look at work volume, then we'll look at transformations. So when the robot is moving in space, we need to find the relation between the end effector position and orientation and the base. So we assign 0, 0, 0 to the base and say this is my base frame, it doesn't move. And I need to find the position orientation of the end effector and all the joints with respect to the base frame, because of which I need to have the transformations that will go from joint to joint. So we will stop here today and continue in the next class, where we'll start off with joints, different kind of joints, and we'll look at work volumes in that order. Okay, so we will stop today. Thank you.